didn't see it. I've been thinking about gas turbines. Would you like to know a little more? Sure you would. First is the air. This air is usually cooled by evaporative cooling to promote higher efficiency. This air enters the compression cycle of the turbine. Here it's compressed to high temperatures and pressures. Next is the combustion section of the turbine. Natural gas fuel is fed into this section and combusts. This heat energy is turned to mechanical energy by the rotation of the blades and vanes. This mechanical energy is transferred to an electric generator, which generates electricity. Next, the hot exhaust gases from the gas turbine exit, very hot, and are passed through the heat recovery steam generator. This heat recovery steam generator is a series of tubes, much like a standard heat exchanger, which changes water into high pressure steam and high temperature steam. Next, this high temperature steam goes to a second turbine, a steam turbine, where it expands, and this energy is transferred through a shaft to a second generator. And then it condenses down here and is pumped back into the heat recovery steam generator. There is also a cooling loop and another heat exchanger associated with the steam loop. And this cooling loop has a cooling tower, which evaporatively cools the cooling water. And that's how it works. But there are some problems with this system. You can get corrosion in the turbine, in the steam turbine, in the heat recovery steam generator, and within the cooling loop itself. So be careful. Another section of the turbine that experiences problems is the combustion section. In this section, the main problem is type 1 and type 2 hot corrosion. Now, I won't get into the details too much, but this type of corrosion is caused by molten alkali salts, which eat through the protective oxide layer and destroy the part underneath. This leads to very rapid corrosion. As you can see here, this part was severely damaged by type 2 low temperature hot corrosion. Now, you may think that high temperature oxidation would be a very big problem in these blades, but in industrial turbines, they generally operate beneath the temperature which this is a problem. So, if the turbine is running hotter than intended or designed for, it can be a problem, but it usually isn't. Now, how can we prevent corrosion in gas turbine blades? Well, there's two main solutions. The first is the use of coatings. These coatings are rich in either aluminum or chromium, and they form a protective oxide layer. The aluminum is generally used for higher temperature blades, and the chromium is used for lower temperatures. This aluminum or chromium can be diffused into the base material, or it can be applied as an overlay coating. These overlay coatings are typically referred to as M-crawlies, and this stands for the metal matrix, which is a nickel or cobalt or both, the chromium, the aluminum, and then some yttrium, which enhances adherence of the oxide barrier to the part. The other way to prevent hot corrosion, type 1 and 2, is to remove the reactants that cause it. The sulfur is usually not economical to remove, so the focus is placed on sodium, potassium, lead, and vanadium. If these can be reduced to the very low parts per million level, hot corrosion can usually be solved.
Good.
Hey, what's wrong, buddy? I just don't know how to determine the extent of corrosion.
Well, I'll show you how to determine the extent of corrosion.
Now you may ask, what are some non-destructive methods for determining the extent of corrosion in combined cycle gas power plants? Well, there are many. The first is magnetic particle inspection. This is when magnetic particles are applied to the surface of a part and then a magnetic field is induced. Flaws in the surface of the part will show up as a pooling of magnetic particles. The next is ultrasonic testing. This is when ultrasonic waves are passed through a part and corrosion in the part changes the wavelength of the ultrasounds. This can be detected by the computer equipment and displayed on a screen. The next, and probably the most important method in determining the extent of corrosion in turbine blades is dye penetrant inspection. Here, a dye is applied, and it is absorbed by the cracks, and it highlights them and makes them easier to see. There are two types of dyes. There's a fluorescent dye, and there's a visual dye. And the fluorescent dye is not usually used because of the corrosion products found on the surface of the parts. Eddy current testing. A wire coil is wrapped around the piece, and it generates eddy currents within it, and these are picked up and then compared to a baseline sample, and differences indicate corrosion or flaws. Radiographic testing is basically X-rays applied to the part, and flaws can be seen on a screen. Visual testing is also very important for turbine blades. Often you can see pitting, and you can see oxidation and hot corrosion. There's also a change in reflectivity of the blades as they corrode. For the heat steam recovery generator, vibrational testing is a very important means to determine the wall thickness of the pipes. As the pipes corrode over time, their vibrational frequency changes. This can be measured and monitored and used to determine how much corrosion is taking place and if the pipes are still safe to use.
There are several different measures that should be taken to mitigate steam turbine corrosion. To avoid corrosion fatigue and stress corrosion cracking of the blades, one should avoid high strength and high hardness alloys. Instead, alloys with high material damping, such as high chromium steels or titanium alloys, can be effective. Blades cannot be in resonance with the running speed. This will lead to high vibrations and greater stress, results in more stress corrosion cracking. Also seen effective is washing the blades with chloride-free water on turbine shutdown. Pitting. Pitting can be avoided by controlling the steam purity. Chlorides and sulfates should be removed, and cation conductivity should be tested. Flow accelerated corrosion can be controlled by regulating the velocity of the steam. For stress corrosion cracking of the discs, local operating stress to the yield stress ratio should always be less than 0.6. For disc rim stress corrosion weld repair, use 12% chromium stainless steel. This has been seen effective. Impurities in the steam should, again, always be kept minimal. It also should be noted that crack propagation increases with yield strength, and stress corrosion cracking becomes susceptible to hydrogen embrittlement.
Flow accelerated corrosion is probably the main problem in the heat recovery steam generator. It's caused by fast moving fluids through the pipes. You can estimate it by several factors. Basically, if you moderate the pH levels and the oxygen levels flowing through the fluid, you'll be able to tell if the solution is going to be more caustic and it's going to go a little bit faster. Also by moderating the materials that are going to be in contact with the fluid. The flow rate and the turbulence also have a really big impact on how much corrosion is going to occur, and the dimensions of the piping. As you can see, the big locations where flow accelerated corrosion occurs is in basically the pipe bends here, where the pressure builds up and they move quickly through those quick bends. That's where you're going to see the most flow accelerated corrosion. And now I'll go over the solutions to corrosive issues in the heat recovery steam generator. Basically, to combat flow-accelerated corrosion, you can regulate the pH using buffering techniques. So with this technique, you can introduce a basic substance, usually ammonia, to change the pH to a level where it's not going to cause corrosion. As you see, in that safe range right there, that's where you want the pH to be. Another thing that you can use to solve some issues is an auxiliary boiler at night. Basically, this will keep the steam at a relatively high temperature to avoid getting to that dew point where you'll start getting condensation on the pipes. Another problem is dissolved oxygen, which results in more flow-accelerated corrosion. Basically, if you regulate the amount of dissolved oxygen, you can eliminate some problems. The only thing you want to make sure is that you don't eliminate all of the oxygen, because then you get removal of some oxidation product on the inside of the pipe that actually protects against corrosion. So the solution to that is called oxygen treatment. Basically, you regulate how much oxygen you put into the fluid, and therefore you can put just the right amount to keep that oxide layer to protect against corrosion, and yet you're still avoiding oxidation products from chafing off the pipe.
Yo, I think we can crack this guy. What do you think we should do?
Alright, man. You be the good cop, I'll be the bad cop. You ready for this, man?
Yeah. Alright, back up, let's go. What do you know about corrosion? I don't know anything!
And I found some solutions to the microbial corrosion and wet corrosion. And there are many ways to protect the metal. The first way is virus corrosion inhibitor. Oh, that's okay. The virus corrosion inhibitors, and another way is biocide treatment programs, just like killing bugs. And the third way is it's easier. It's just a regular mechanical clean. And the third way is conveyor drainage and dry storage. And about another one, and there are more ways and to solve this problem, and such as anti-corrosive paint coating and hot dip galvanizing and electroplating and spray galvanizing and cranial plating and aluminum spray and rubberizing and coil coating of sheet steel. Yeah. What do you think, Brad? What do you think? So you think I'm right? Oh. Oh, that's it.